Hello everybody, I'm here with an example of a three-dimensional particle equilibrium where we are told that this balloon is being held by three cables, as you could see, and the force, the uplift force is given to be 800 newtons, so this force here is equal to 800 newtons. So basically these three cables have to support the 800 newtons. And the objective here is to find the force in each cable, okay, AB, AC, and AD. So what I did actually, I went ahead and put the coordinates of these different points because we're going to use them to determine the unit vector of, along each of these cables and use that to describe the force in the Cartesian format, okay? But let's just draw a quick free body diagram, guys, here. So we know that the force here is 800, right? So this force is 800. And then our objective is to find force in cable AB, force in cable AC, and force in cable AD, right? So this is what we call concurrent forces. So forces that pass through the same point. So we have the F, which is 800, and then three unknowns. Three unknowns, and then we have three equations, right? A three-dimensional particle equilibrium. So we have to basically balance forces in the X, sum of the forces in X equals 0, in Y equals 0, and in Z equals 0. Three equations, three unknowns. So the way we're going to describe each force vectorially or in the Cartesian form is very simple, guys. All you have to do, for example, for FAB, whatever the magnitude of AB is, which we don't know, we're trying to find that, right? We multiply it by the unit vector from along AB. And how do we find unit vector along AB? So let me just do one of these so you can follow the same format, the same process for the rest of them. All right, so all you have to do to find the unit vector along a line or a certain direction is to first find the position vector that goes from the initial point A to final point B, right? So that's RAB, position vector, divided by the length of the vector, and that's how you get a unit vector. And then what is a position vector? Just look at the coordinates of A and B. A is initial, B is final. So you have final minus initial. So minus 1.5, minus 0, I, right? The unit vector along x-axis. Minus 2, minus 0, J, and then finally 0 minus 6, K. And when you clean that up and you divide by the length, let me actually do it down here, so I'll put the length for you in a minute. Minus 1.5 I, sorry, minus 2J, and then minus 6K. And what would be the length of this? The length of this would be the square root of sum of the components squared, which in this case, I believe it becomes 6.5. So your UAB becomes minus 1.5 I minus 2J minus 6K, right? Divided by, as I said, 6.5. So now let's try to do this, right? As I said, you want to describe a force vectorially, right? Or put it in the Cartesian form. You just take the magnitude and you multiply it by the unit vector along the line of action of the force. So that's called line of action. RAB is the line of action of the force. And you could leave it like this or break it in individually. So for example, you could, so the x component is minus 1.5 over 6.5 FAB. That's the x component times I. Similarly, minus 2 over 6.5 FAB J, and then finally minus 6 over 6.5 FAB K. Okay? And we're going to do this for every one of these. So we're going to do it for FAC and FAD. We already did it for FAB. So let me go ahead and go to the next page. I put the these coordinates of these points once again for you, and then we can go ahead and find or describe the other forces, FAC and FAD, in the Cartesian format. All right, so I'm going to move to the next page and show you, going through the same process, show you how you can get the other forces put in the Cartesian form. So I've already done this for you here. So, for example, FAB, we already had it from the last page. That's how we described it in the Cartesian form. So you see the coordinates of the points right here. So I do exactly the same thing for FAC, right? So FAC magnitude times the unit vector from A to C. So I just did final minus initial. So final is C, initial is A. So 2 minus 0, right? 2 minus 3 minus 0 minus 3. And then finally 0 minus 6, right? 0 minus 6. Okay, and so then I broke it down individually. This is your FAC, and then did the same thing exactly for FAD, guys. Described FAD vectorially or in the Cartesian form. Notice that FAD doesn't have any x component, so it's 0. But I just put intentionally 0 there so that it's a two-dimensional, basically, vector. Okay, so the next step is to add all of these, or actually just take x component of each one and add them up, set it equal to 0. The y component, add them up, set it equal to 0, and so on, z component. But let me just, one last thing, show you here. What about this one? This force F vectorially would be what? 800 is the magnitude pointing in the positive z direction. So that force vectorially would be what? That's the uplift force, is 800K. So don't forget about this force. So basically, vectorially, what we have to do, we have to say FAB as a vector plus FAC plus FAD plus this force F must be equal to 0. So basically, the resultant of these four forces must be equal to 0, which then you could write it like that, but eventually it boils down to what? Just adding all the x components, say it equals 0, y component equals 0, and z component equals 0. And then we get 3 equations with 3 unknowns, right? FAB, FAC, and FAD. So let me go ahead and set it up for you, and we'll try to solve it. So here we go. I set up the equations, so I just added all the x components, say it equals 0. I call that equation number 1. Did the same thing for y components, and then the same thing with the z components. So now we have 3 equations, 3 unknowns. Solve this any way you like. You could, use the substitution method. In other words, reduce, get FAB in terms of FAC and plug it into the other equations. Get a 2 by 2 eventually and solve it. Or even form a matrix. So let me go ahead and show you in the matrix form and then finally give you the solution. Okay, so now we have put these 3 equations in the matrix form. And all I did, I just looked at the coefficient of each one, as you could see here. No FAD here, so 0. And then all I did here also, I moved this 800 to the other side. That's why I got minus 800. And the right-hand side of the first 2 equations are equal to 0. Okay, so let me give you the final answer. Solve. And the tension for the force in cable AB comes out to be close to 251 newtons. Cable AC is equal to 203 newtons. And then finally, cable AD comes out to be 427 newtons. So as always, thanks for watching and listening. And if you like the videos and you want to see more videos, please subscribe, and you will see, hopefully, more videos every week. And thanks for watching.